Hello, my name is Wyatt Groves, and I'm going to be talking about switching power supplies. I'm going to go a little bit into the history, why they're used, why they're important, and how they're different from the linear power supplies that we've learned about. Now, let's get a baseline for what is a power supply, because I think it's important that we all understand where I'm coming from. So, I've always thought the name power supply was a little bit of a misnomenclature because to me, supply kind of evokes imagery that it's creating power of some sort, when that's not really the case. It's more that it's converting what it has into something a little bit more useful. For example, maybe it'll convert the 12 volts from your wall into, or the 120 volts from your wall into 12 volts that you can use to maybe charge your phone. Now, there are two types of supplies that you'll generally find out on the market, and these are the switching and the linear power supply. The switching power supply is what I'm going to talk about, and the linear supply is what we learned about in maybe electronics or circuits 3. Now, the switching is generally considered to be a better power supply, but they're a bit more complicated, and you'll find that there are others out there. For example, IBM used to use one for their supercomputers back in the 70s, and it was based on motors. And it's sort of like trying to charge your phone using your car. Yes, it's useful, but only in specific scenarios, so mostly you'll find switching and linear supplies are the ones that are used. Now, let's talk about the original power supplies on the market. The first ones came about in around 1920, a little bit later, and you'll see on the right here is a image of an ad that was posted for one of these power supplies. Now, the main component that allowed these power supplies to run was what was known as the voltage regulator tube. Essentially, this was just a vacuum tube that they would fill with an ionizing gas, and it would act like a Zener diode. Now, the switching power supplies came about in 1958, and these were some of the first ones that were created. The idea was around for a little bit before that, but they first became on the market in about 1958 from IBM. You would also notice that later on these would get a little bit better and they'd be used by the Hewlett-Packard company, and they used those for their calculators. But it wasn't until 1976 that the first time the name switching mode power supply was used in a patent. You'll find a lot of companies out there that they all claim to be the very first ones to use the switching power supply or to create the switching power supply. It's very murky, there's a lot of conflicting information, so it's not 100% clear who the first person is. But you can generally think that about 1960 was when they started to become a little bit more well known and a little bit more used. Now, why were these new supplies so good? What was so special about them? Well, the original supplies that were used, the linear ones, had a pretty low efficiency. They were only about 50% efficient on average, which is pretty bad. They were also very big and they were very hot. They had these massive heat sinks on them to try to dissipate this heat, but it wasn't ideal. So let's go a little bit into how these old ones work just so that we know what's going on, and you should be very familiar with this information. Now, the only major difference here from what we learned in our electronics or circuits 3 class is the Zener diode was a vacuum tube, and then eventually, of course, it did become the Zener diode. So we should all be very familiar with this, know what's going on, know what to expect. The upside to these is they were pretty easy to build, simple to understand, so that's typically why they were used. Now let's move on to the switching power supply. Now, the switching power supply has one key difference right off the bat that you'll notice. There's no transformer at the input. Instead, it is directly rectified. And then it's put through this high frequency switch, and it's transformed after that. And then it's rectified again. And this switch is, of course, controlled by this control circuitry, which we'll go into in a little bit. Now, if you'll notice from these graphs here, we start out at our maybe 120 volts, let's say, and then that gets rectified to this very rippled voltage. And then essentially what we're doing is we're sampling this rippled voltage at a very high frequency. This can be around 2000 hertz all the way up to in the megahertz range, and depending on what you specifically want from your power supply. Because we sample so fast, we're able to create this artificial square wave here. And then we can put that through our transformer, and then we can rectify that to create this nice linear DC output. Now, the rectification, the transformer, and the other rectification are almost identical to what we have already learned, what we're already familiar with from the linear supplies. The key is this control circuitry here. Now, let's go into this control circuitry a little bit. So the control circuitry is essentially just a switch. If you'll think about it, if you were to close this switch and just leave it closed the whole time, the problem you would run into is that we wouldn't be able to get anything useful out of this transformer. Because the transformer needs this alternating current so that the magnetic field can be induced. Now, if we have just a small ripple, it might not do anything, or it might just have very minor effects and nothing useful would be coming out of this. However, because we're able to sample at such a high frequency with this, we're able to artificially create an AC current and artificially create a field here that can be rectified, that can go through this transformer to then be rectified. Now, turning this switch on and off very quickly is the whole point. That's all that the control circuitry does. And there's a bunch of different ways to do this. They're generally simple to implement, maybe an IC or a bank of capacitors and resistors and some inductors. But all that you need to understand is that this switch needs to operate at a very high frequency so that we can get our square wave out of it. Otherwise, it doesn't work. Now, let's talk about this in terms of the real world so that we can get a better understanding of what this would physically look like. So on the right, here is a picture of a disassembled switching power supply. And this one is a small unit, only outputting about 1.5 amps. So let's start at the input here. We have our input, and that goes into our diodes, 1, 2, 3, 4, 1, 2, 3, 4, and then it goes into this capacitor here. And that is the first part of our switching power supply. This is the rectification here. Now, then we'll notice we have these two ICs here. These are what control this switch and the control circuitry. And then we have this big black box here, and this is just our transformer. And then we have our final rectification here, and then our output. And we can see that here. Now, linear supplies nowadays, typically, unless you're buying a very fancy unit, have an efficiency rating around 70 to maybe you'll see some at 75-80%, but typically 70%, 60% is a pretty good estimate. The switching supplies, as you can see here from the 80 plus standard, are usually around 85 to 90%, which is much, much better. And these aren't even, the 85-90% isn't even the highest end. Those are low to mid-range. And it does this while making much less heat. Now, what allows these supplies to make much less heat and have this higher efficiency? Well, if you'll remember, the linear power supplies, whenever they go over their rated voltage, they will burn off all of that excess power through a resistor. or sometimes a transistor, depending on the specific application or the specific design of the supply. But it'll burn off all that extra power through that resistor. The switching supplies don't do that as often. Because they're switching so much and they're operating at such a high frequency, they only burn off a little bit of power every now and then. So they only burn off power on some of the cycles. Also, because they're operating at these very high frequencies, they're able to get away with using much smaller capacitors and much smaller inductors. So, those components are also not producing quite as much heat. This also allows you to use smaller, or because those components are smaller, this also allows you to make the entire supply smaller. Now, this doesn't come for free, of course. Nothing can ever be free. The downsides to this supply are that they're very, very complicated to build in comparison to a linear supply, and they're also very, very finicky. A lot of times, if something goes wrong, it's very hard to replace, it can be very expensive in comparison to a linear supply, or the system will just stop working altogether. Whereas with the linear supply, if something stops working properly, the supply is more likely to keep working somewhat, or it's very easy to replace. Because these switching supplies also use ICs and they can use a lot more components, they can get expensive quick, depending on how efficient you want it and how good you want it. So they can get a bit expensive. Now, if you'd like to fact check anything, or if you'd like to learn a little bit more about the topic yourself, I've included a list of references that includes everything that I used to figure out what was going on, learn everything new, and all of that sort of stuff. Thank you so much for your time, and have a great day.